Good afternoon. 5/11, May 11th, 2023. Oftentimes when one writes out the month and day, there's various ways to write it, either day month or month day, or year month day, or month day year, and this kind of thing. And I tend to write it as year month day because then it's naturally ordered lexicographically, with the general idea that with regards to the days of the week and this, and otherwise comes from the world of computer programming and the locale of the formatting of dates. It's variously that what is readable or legible or expected, then gets into how things are sorted and arranged and aligned in terms of brackets and buckets and partitions, in terms of clock time, say the second since midnight, when the midnight's the epoch, or the second since January 1st, 1970, when that's the epoch, 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 or when that plus 18,262 days is January 1st, 2020, 50 years later, basically the modern epoch since 2020. These are the kinds of things that one gets into when studying the formatting and arrangement of time series data and the values of time in machine integers of the usual milieu of the C runtime of usual operating systems and various real-time systems. So today I'm thinking to read a bit more about the differential, and what I found today was this great little book called Fourier Analysis and Boundary Value Problems. And I have about 20 or 30 books on ODEs and PDEs and boundary value problems and initial value problems and various approaches and all this kind of stuff. This one's pretty cool. He's got Enrique A. Gonzalez Velasco has written this book, and it was published in 1995 by Academic Press. So that's a pretty nice mark. And then what there is a bunch about Fourier. And so it talks about Fourier's approach to his initial solving the problem of the radiation and conduction of heat, and this kind of thing. But then it gets into a whole usual course of the linear development of a usual linear curriculum that these days is still often kind of figured out, gets into stuff like the orthogonality of sine and cosine. What does it mean that sine and cosine are orthogonal to each other's functions? Well, it means that they can be composed and decomposed in various systems of otherwise equations. And what is Graham-Schmidt, and what are these things with due to convergence and uniform convergence and laws of convergence in the large and small and the weak and strong. These are various kind of things that get into why there's lots of great stuff in them. Talks about Bessel functions and Fourier-Legendre series, the Legendre polynomials, Poisson's integral formula, the cooling of a sphere. That's kind of interesting. With regards to whether it's heating or cooling, there's these ideas about the first and second law. They get into various differences. In terms of what here has been framed as the restitutive and oscillating, that whether something that has a tendency towards the restitutive is that it returns to its original form. Then if it always has overshoot, then it results oscillation. So you can think of periodic motion as just a restitutive form with a constant amount of overshoot. And whereas something like thermal coefficient of expansion or something like that, depending on the temperature, is just restitutive and without the oscillation. Then there's this other notion, the dissipative and the attenuative. The dissipative basically leaves the system. But that similarly, though, you can kind of look at some ways like a restitution without oscillation is sort of just an attenuation in terms of whether it dissipates and whether it attenuates to zero. And so there's an idea for attenuation, whether it attenuates to zero or the floor, and when in terms of when there's dissipation, what basically reduces for a lot of these regular systems of periodic motion or motion in fields with either astability, not having a stable equilibrium where the forces aren't equal to each other, thus the results that there is a static state. The dynamics of the state, and when there are systems that always have dynamics, then that can be reduced to a static of the state. these are the things you want to get into and thinking about usual complements and complementary duals. And so I found those kind of descriptive. And so this book starts, and it's got a great little preface here. This is a book about the solution of BVPs, boundary value problems, involving the linear PDEs that appear in modeling many natural phenomena in engineering and physical sciences. This kind of goes back to everything in the differential is called dynamical modeling. In particular, it's about Fourier analysis. Now, one thing I really need to refresh in my memory is the difference between Fourier series and Maclaurin and Taylor series, because they're quite different things, yet they also get into the same notions about the telescoping and the infinite series and the order of terms. I've enjoyed reading this so far. I only got a few pages into it. Many pages of this book are devoted to historical material. There's included an elementary proof of the convergence of double Fourier series. So it begins starting with a description and a picture of Joseph Fourier, or Fourier. It's kind of pronounced like a Fourier is, but it's Fourier, or Fourier, or Fourier. Talks about his position with Napoleon Bonaparte. Fourier, he returned to France at the École Polytechnique. There's kind of three big schools in France. There's the engineers school for the military, there's this kind of a science school, and then there's like one other school. Those are kind of the big three schools in Paris. And then he wrote Memoir sur la propagation de la chaleur, an essay about the propagation of heat at the Institut de France. The methods that Fourier used to deal with heat problems were those of a true pioneer because he had to work with the concepts that were not yet properly formulated. He worked with discontinuous functions when others dealt with continuous ones, used integral as an area when integral as a prederivative was popular, and talked about the convergence of a series of functions before there was a definition of convergence. Now, I'll be curious to find out what the prederivative is in terms of how to deal with that as the higher order, or the inverse of taking the derivative is the derivative in terms of the integral. The methods that Fourier used to deal with heat problems would prove fruitful in many other physical disciplines such as electricity, acoustics, and hydrodynamics. It solves a bunch of the inverse square type stuff. It was a success of his work. The memoir was not well received. A committee consisting of Lacroix, Lagrange, Laplace, and Monge was to judge the memoir and publish a report on it, but never did so. Instead, criticisms were made personally to Fourier, either in 1808 or 1809, on occasion of his visits to Paris to supervise the printing of his Préface historique. His title was personally chosen by the former first consul that had crowned himself Napoleon, to the Description de l'Egypte, a book on the Egyptian discoveries. The criticisms came mainly from Lagrange and Laplace and referred to two major points: Fourier's division of the equations of heat propagation and his use of some series of trigonometric functions known today as Fourier series. Then Biot, Jean-Baptiste Biot, published some new criticisms in the Mercure de France, a fact that Fourier resented and moved him to write in 1810 angry letters of protest and pointed attacks against Biot and Laplace, although Laplace had already become supportive of Fourier's work by 1809. In one of these letters to unknown correspondents, he suggested that, as a means to settle the question, that public competition be set up and a prize be awarded by the Institute to the best work on the propagation of heat. If not because of this suggestion, it is at least possible that the Institute considered the question of a prize essay on the theory of heat in view of Fourier's vigorous defense of his own work. Fact is that in 1810, this was the subject chosen for a prize essay for the year 1811, and Laplace was probably instrumental in converting Fourier's suggestion into reality. A committee consisting of Huy, Lagrange, Laplace, Legendre, and Melas was to judge on only two entries. On January 6, 1812, the prize was awarded for Fourier's theory de mouvement de la chaleur dans le corps solide, an expanded version of his 1807 memoir. However, the committee's report expressed some reservations. This essay contains the correct differential equations of the transmission of heat, but both in the interior of solid bodies or on their surface, and the novelty of the subject added to its importance has induced the class to reward this work, but observing meanwhile that the manner in which the author arrives at his equations is not exempt from difficulties, and that his analysis to integrate them still leaves something to be desired in the realms of both generality and even rigor. So, it's often so that the engineering and the physicists come in and the mathematicians really want the rigor because they want to make sure that it's not possible to arrive at ambiguous conditions or the violation of guarantees or that the behavior is not well defined, that the formulas and functions are not well behaved. And because so many systems in the differential have many starting points and many solutions that result how they come out, in some cases that there's even infinite possible solutions and they're defined, it's underdefined or under-constrained, the equations so indicate one instead of just a family of them, that it gets into the general and the particular or the specific and these inner and outer products, so these complementary duals, all these kinds of things. This will show the originality of his methods and also the nature of those insidious analytical difficulties, as they were referred to by some of Fourier's opponents. So it talks about the heat equation. It's a piece of metal on the x-axis. It's outside as an insulator, so it's air or some other notion of a medium that does not transmit heat, while as the metal uniformly transmits heat. Up to metals that, for example, like water, for example, always has the same temperature everywhere in a body. So this is kind of the old, you can't burn a paper cup full of water because until the water boils off, its temperature is maintained at most its boiling point until it converts to steam. So it illustrates kind of three kind of media. One where is the insulator, like air. It basically does not conduct heat, but though heat has radiation and convection, conduction, and one other one, sort of radiation, convection, conduction, ... Where the idea is that in various media, heat is a kinetic thing, and it's described often as the vibration of the molecules and the propensity of them as a gas to repel each other. Whereas for liquids, it's like that which leads to the boiling point, or that which leads to the freezing point. And then for solids, it's generally the idea that it won't melt, if not burn. And it varies in terms of the chemistry of things, I suppose. The temperature varies so smoothly in time and along the bar that the function u has continuous first and second partial derivatives with respect to both variables. This is that at any given time t, all the points of abscissa x have the same temperature denoted by u x sub t, and the bar has uniform cross-section whose area is denoted by a and constant density rho, and the bar is insulated so there's no exchange outside. In order to derive the desired equation, we shall apply the law of conservation of energy to a small piece of the bar, the slice situated between the abscissas x and x plus h. This is just what it drops to the line, or it's the same kind of like the point along the bar. It's shown that if C denotes the specific heat capacity of the material, which is defined as the amount of heat, the usual name for thermal energy, needed to raise the temperature of a unit mass by 1 degree. And if the temperature u sub t were assumed to be the same at all points of the solid, then the amount of heat in the slice of volume AH at time t would be Qt equals CpAHUT. The constant times, C rho, A, HUT, a constant times this constant density, and times this specific heat capacity, so that's the capacity times the density, times area, the cross-section, times the distance between point to point, times u sub t. That would be the Q sub t, the amount needed at one end of the bar to raise it along the way. Oh, so though it's an additive in H here, it's a multiplicative constant in H in this it's moving it from T to in T in from X to X plus H, where we have implicitly assumed that there's no heat at absolute zero temperature. But in our case, the temperature is supposed to vary not only with time, but also from point to point along the bar. Thus, the heat in the slice must be represented by the integral, and this is how it dissipates, how it attenuates. The amount of heat, Q sub T, is the integral from X to X plus H, or this difference, of the constant, or the capacity, times the density times the area of mu S comma T ds. So it's gone from U sub T to U S comma T. If U sub T denotes the partial derivative of U with respect to time, the rate at which this heat changes with time is Q prime T equals C, the integral from X plus H is C rho A U sub T, S comma T ds. That otherwise, that partial is the other partial, and it's in time, so that's why it's represented that the quantity of heat at a given point at a given time is like so, in terms of otherwise like a blob of heat. What is a blob of heat? Well, a blob is an amorphous region, and generally it indicates that it grows, and then that when it's deformable, and then it fills an area. So here's the quantity of in the entire thing is a function of the point at any one time. So it's setting up to solve this in reverse, or solve this in inverse kind of thing. And instead of kind of describing how it dissipates. The formula that can be contained directly. Now, the only way for this heat to enter the slice is through the sides at X and X plus H. So it's only dealing with a section of this bar. Or by internal generation, which could happen, for instance, by resistance to an electrical current or an inductive element, heating element. If heat is generated internally at a constant rate of Q per unit volume, then the heat is generated at a rate Q A H in the slice. If heat is generated internally at Q per unit volume. Finally, to consider the contribution through the sides of the slice, this is where the volume was density over the area as well. Finally, to consider the contribution through the sides of the slice, Fourier assumed that the rate at which heat flows through any cross-section per unit area is proportional to the temperature gradient. So that is proportional to the gradient means that it's big O proportional, it's little o proportional, theta proportional. It's proportional in the sense of differing is only by some constant, that an input increased linearly on one side will affect a linear change on the other side, so proportional in the linear. Fourier assumed that the rate at which the heat flows through any cross-section per unit area is proportional to the temperature gradient. So it's saying that the bigger the difference in the temperature, the more it will flow over, the more there's potential. So you can also frame this in terms of kind of like a potential instead of that it's so proportional there. And so then figuring out that gradient is kind of the same thing as that the gradient would be the function instead of that the function is a gradient. Again, in this world of complementary duals where we're looking for the theory of some potentials with regards to the classical and this kind of definition of action. Accordingly, heat flows through the sides at the rate negative K A U sub X X comma T and negative K A U sub X of the quantities X plus H comma T. The proportionality constant K is called the thermal conductivity of the material and is assumed to be positive. There are certain junctions like Seebeck and Peltier junctions that can exchange heat for the electrical potential and potential in the electrical for heat. They basically convert them. So you can, for example, apply electrical activities to something like that, and it reduces the temperature. The Seebeck and Peltier junctions have some pretty interesting things about the effect they have that is electromechanical in a sense, how they operate. And then the idea of something like thermal conductivity is that in liquids like water, that the thermal conductivity is high, meaning that when you boil the whole body of water, it ends up having the whole temperature everywhere, however it so does. That's just one of those interesting features about water. Then it makes for like the triple point of boiling and freezing and all the steam tables and all that kind of stuff, rather interesting. This is where the first law of thermodynamics is a lot about steam tables and the Carnot cycle and all this kind of stuff. And then the second law is about the entropy or Clausius and da. And so they're different things, and the one about these bodies reflects something else than about the particles, and it's a thing. The proportionally constant K is called the thermal conductivity. Then the negative sign expresses the fact that heat flows in the direction of decreasing temperature. That is to the right, where U sub x less than 0, to the left when U sub x is greater than 0. The law of conservation of energy, which is of course valid for heat rates, is then expressed by the equation, the integral from x to x plus h, where between these two sides, given it's fixed at one side and fixed on the other side, that this integral of this quantity of 0 a u sub t of s comma t ds equals q of ah minus k a u sub x x comma t plus k a u sub x x plus h comma t. So that's set it up as an identity about the differences in terms of these thermal conductivity and heat capacity. So what are the material properties so developed that otherwise you just imagine a uniform thing, and it's what's its thermal capacity? 1. What's its conductivity? 1. And then the otherwise, these are the kinds of things that end up making for this identity that it's about this. It's basically framed in the middle in terms of this h, which is this difference, which is going to be made small and acted upon as by the same usual method as of finding a line that reflects it in terms of the midpoint theorem and the intermediate value theorem and this kind of thing with regards to h going to 0. That again, that it's going to be read up quite this way. Dividing by AH and finding the limit as h goes to 0, we obtain limit as h goes to 0 of 1 over h of the integral of x to x plus h of 0 u sub t s comma t ds equals q, where AH is dropped out, it's reduced the order of it, plus k, and the limit h goes to 0 of u sub x x plus h comma t minus u sub x x comma t over h equals q plus k u partial or xx x comma t. But the left-hand side is recognized to be the derivative of integral from 0 to x of 0 u sub t s comma t ds with respect to x, which is known to equal 0 u sub t x comma t by the fundamental theorem of calculus. Hence, the temperature distribution in the bar is described by the equation 0 u sub t x comma t equals q plus k u sub x x x comma t. If we define a new constant, k equals little k equals big K, all the previous was big K, k or kappa say, k equals kappa over 0 greater than 0, that this constant is greater than 0, called the thermal diffusivity of the material. This is what I'm looking for, is the diffusion, called the thermal diffusivity of the material, which is this material's thermal conductivity divided by this heat capacity and the density of it for where most volumes in matters like solids and liquids, their density is a product of the material, so it would be a constant for the material, but it depends as a function of volume when, for example, it has or hasn't thermal expansion. That writing the thermal diffusivity this way as a constant in terms of the proportionality of the conductivity of the material and the capacity of the material is as of a filling. So it's kind of just having along the lines at each point in this area, you describe how much it takes to fill it and how much is full, and then how much it goes or falls off to the sides either way. The given stack of heat counts or tallies appropriately high always slides to the left or slides to the right, depending on, it just slides on either side where it's less. So that's a pretty usual thing. The simpler form of this equation, then when there's no internal generation of heat, U sub T x comma T equals K U sub x comma T is called the heat equation or the diffusion equation. So he's taken out where there's no internal generation of the heat or hot points, hot spots. This derivation is somewhat different from the original one by Fourier. However, although it is still true that a small imperfection still existed in his treatment in the 1807 memoir, it is well to remark at this point that there was already nothing wrong in the derivation contained in his prize essay. Before presenting Fourier's method of solutions, we shall make some general remarks concerning this type of problem. And section 1.3 is boundary value problems. An equation involving a function of several variables and some of its partial derivatives. And so trying to solve things in terms of differential equations and setting them up on the one hand in terms of the partial derivatives is also trying sometimes to make it in terms of the antiderivative, the integral, in terms of then figuring out what those constants would be to come into it. And I have studied only a few college courses for ODEs, PDEs, boundary value problems, and after initial value problems, only like 6 or 9 credits. But and then a lot of the stuff that follows was in terms of dynamical modeling that uses these same things, or in calculus and physics that have these same kinds of sets up for physics. It's like so. And reading from Gonzalez Velasco, an equation involving a function of several variables and some of its partial derivatives, such as the two derived at the end of the previous section, is called a PDE. And a function that satisfies the equation is called a solution. We shall take the heat equation as our starting point. Besides the trivial solution, U equals 0, it is easy to see that U sub 1 of x comma t equals x, U sub 2 of x comma t equals x times quantity x squared plus 6kt, and U sub 3 of x comma t equals e to the negative kt cosine x. And this gets to where I need to refresh my memory about ln x and the integral and derivative of the inverse, and getting into some ideas about how things can be solved in terms of some projections and spherical symmetries about the antiderivative. But here this third partial is in terms of e to the negative kt, where the k is this constant, is so defined and derived in terms of the diffusivity constant of times cosine x, and u sub 4 x comma t equals 1 over root t e to the negative x squared over 4kt, that quantity, e to the all that, are also solutions. So, okay, so these are all different solutions that also are of the same thing. Moreover, it is easily verified that the sum of two solutions and the product of one of them by a constant are also solutions. Which of those represents the actual temperature distributions in the bar? So this is where the values come into the problems. The unavoidable answer to this is that the question itself is not well posed. The temperature on the bar will also depend on several additional conditions. For instance, from a certain time on, these temperatures will depend on the initial temperature distribution at the given instant. And although the bar is insulated along its lateral surface on any amount of heat that may enter or leave at the endpoints. Therefore, we see that both initial conditions and boundary conditions will affect the actual temperature distribution. These conditions can be specified in a variety of ways. For example, the temperature may be given at t equals 0 as a function of x, u x comma 0 equals f sub f of x. And it may be further specified that the temperatures at the endpoints u of o comma 0 comma t and u of a comma t will remain fixed for t greater than 0. This can be accomplished, for instance, by the application of electric heaters with well-regulated thermostats at the ends of the bar. A problem consisting of finding solutions of a partial differential equation subject to some additional and boundary value conditions is normally referred to as a BVP, boundary value problem. The initial values are just like for a given parameter, and then a boundary value is a function on one side or in the area of the integration or the system. In order to pose some boundary value problems for the heated bar, we shall find the following notation and terminology to be convenient. Suppose that the bar is located between x equals 0 and x equals a, and if r squared is the Euclidean plane, to find the sets. D equals x comma t and r squared, where x is between strictly 0 and a, and t is greater than 0, and then d bar is that with inclusive equals 0 is less than or equal to a, is 0 is less than or equal to x, less than or equal to a, and t greater than or equal to 0. Then a real value function is defined and has continuous first order, second order partial derivatives, and d is said to be class C2. So C, the class C of these continuous functions, is those with the derivatives, and if partial, each of those defined up to that order. And so a C2 function might be C inf t or whatever, but the class of C inf t functions are infinitely differentiable. Example 1.1, the problem of finding a continuous function u in d bar goes to r that is of class C2 in d, and such that u sub t equals ku sub xx in d, and u 0 comma t equals 0, and u a comma t equals 0 at t greater than or equal to 0, has a solution u of x comma t equals e to the negative pi squared kt over a squared times quantity sine pi over a x. This is easily verified by differentiation. So we have differentiation, there's integration by parts, there's product rules, there's chain rules, there's lots of different rules that enable one to compute the derivative as a function and then to plug in numbers and get out of it what it is. And then when it's partial here with respect to x and it comes out, the second order derivative is like so. This is looking like one of these harmonic functions in a sense, and something I need to confirm because there's only, of course, there's only proper definitions in mathematics, and any mistakes are my own. But I have gone through similar exercises before, so I'm just kind of refreshing myself. Sometimes the boundary and initial conditions are given as limits as a boundary of the domain of definition of the equation as approached in a perpendicular direction. Example 1.2, the problem of finding a function u of d to r, the real line, that is of class C2 and d, such that u sub t equals ku sub xx. So it's about this land of the Laplacians, the second order PDE in D, and then u of x comma t goes to 0 as x goes to 0, t greater than 0, and u of x comma t goes to 0 as t goes to 0, u between x and a. Has a solution u of x comma t equals x over t root t, or t to the 3/2, e to the negative x squared over 4kt. So you see that 4kt a lot, and you see pi over a lot in these kinds of solutions, and they have to do with the trigonometry is about the Fourier series, and the e to the negative x squared with regards to what is an example of a solution that is its own antiderivative. So you can often find e to the negative x cropping up in these solutions, as is verified by differentiation. Note that u is not defined for t equals 0, but has the required limit. This is one reason why the boundary conditions may be given as limits. It allows us to exhibit solutions that would otherwise not exist. A close look at these examples will show that the care must be exercised in specifying the boundary conditions. Each of these boundary value problems also admits the trivial solution u is approximately 0. Besides, for any positive integer n, the function u of x sub t equals e to the quantity negative n squared pi squared kt over a squared sine n pi over a x for any positive integer n is also a solution of the problem in example 1.1, as will be carefully shown in section 1.4, which then is a solution that in each case represents the actual temperature distribution on the bar. The fact is that one expects a well-posed physical problem to have a unique solution. If more than one solution of its mathematical counterpart exists, we infer that the given conditions are insufficient to determine which one represents the answer to the problem. In the case of example 1.1, the insufficiency consists of not having specified the initial temperature distribution at t equals 0. If we require that u of x comma 0 equals sine pi over ax, then only the solution on page 6 satisfies the complete boundary value problem. In fact, it will be shown later that no other solution is possible. Now, when there's described uniqueness results, I'm particularly interested about the infinite case and the semi-infinite case, for example, and the non-standard case. In example 1.2, the temperature at the right end of the bar has not been specified for t greater than 0. If we require that u of x comma t goes to 0 as x goes to a, then the first proposed solution must be discarded because it's not 0 as x goes to a for t greater than 0. Under the given conditions, it is to be expected that the trivial solution u equals 0 will be the answer to the complete boundary value problem. Of course, in any given situation, it must be proved mathematically that the solution of the problem is unique. So here the author goes quite a way to help explain what I put forward as kind of these the constraints of the systems and what is the guarantee of the existence and uniqueness. And that's, of course, just a regular course in solving any number of boundary value problems, initial value problems. And it's kind of reflected in when we were reading about the solution using symmetries of this book right here, about the toolbox of the differential analyst, that there's a lot of techniques and a lot of methods because there's really quite a grab bag of things involved. There is still another requirement, the physical considerations imposed on the solution of a BVP. This is that they must have real values. Physical measurements or observations of the initial temperature of the bar would result in only approximate values. In a similar manner, the temperature at the endpoints cannot be maintained with perfect accuracy. Thus, the mathematical formulation problem will contain small errors in the initial and boundary values. The corresponding solution can only approximate the true one. What we must require is that it be a good approximation. That is, if the initial or boundary value changes by a small amount, the solution of a well-posed problem should change by only a small amount. Now, where that's so, it kind of doesn't necessarily reflect that when you have the system reflecting it otherwise that is closed form to some other application. This is kind of to fit with the hypothesis of small perturbations, the variational principle, the variable principle, to make it so that it's amenable for use with various divide and conquer methods to compute the things and crunch the numbers and all these kinds of things where it's a good thing but not necessarily so, but only in a particular contrived reason. But mostly the solutions have to have values that are sensible in terms of that. For example, if the solution is posed in a space where the solutions come out in the complex numbers and it's not one, that unless there's some interpretation otherwise about the value of that is what's otherwise, a real number, it has to be that. So he goes on to say, Jacques Hadamard, and Hadamard is familiar, for example, as like Stirling. He found a formula that approximates n factorial, n times n minus 1 times n minus 2 times dot dot dot. In terms of Pockhammer and the rising and falling factorials, Hadamard's gamma is kind of like n minus 1 factorial, but it's also defined on real numbers, sometimes complex numbers. And Stirling has one too. I've found an approximation of the n factorial that I've never found otherwise. Jacques Hadamard of the École Polytechnique is credited with first realizing that this condition should be imposed and with exhibiting the first example of a boundary value problem whose solution does not satisfy this requirement. Again, just per my comment just now, it has a counter argument. For the case of the heat equation, the following example, originally given by E. Rothe in 1928 for an ideal bar of infinite length, shows a violation of this condition. Consider the boundary value problem. U sub t equals k u sub xx between negative infinity and infinity, and u sub x comma 1 equals f of x for x from negative infinity to infinity. If f equals 0, then u equals 0 is the solution. But if c is a small positive number, and if we define f of x equals c sine the quantity x over c root k, then the problem has a solution. U of x comma t equals c e of 1 minus t over c squared times sine of x over c root k. By choosing c small enough, f can be made as close to the zero function as desired. However, if u less than t, or if 0 less than t less than 1, the solution does not tend to the trivial solution as c goes to 0. Instead, it becomes unbounded. Thus, a small change in the initial condition from the zero function to f results in a large change to the solution. It gets faster. In conclusion, or it might be where it's faster, or for example, that attenuation is gradual and proportional and constant, or that it falls off. It's just kind of like when you find the gradient, it's like that's a straight line at that point. But in terms of how it goes from minimum to maximum, there you can find any number of solutions that have a minimum and a maximum, and if you draw a straight line between them, it would look like that gradient, but could, for example, drop almost all the way to the floor and then have a long tail out. Or otherwise, there's any number of reasons to consider why there's a real physical attachment or a physical interpretation of the model that a boundary value problem like this would have this kind of otherwise setup, or that it could be so parameterized in the implicits to make for it so a case why this kind of region has an integrable character according to some other constraints that define things in terms of some higher order solutions of rate and drop off, or hysteresis, or otherwise what results the long tail of some of these kinds of things, with regards to otherwise it's all linear and well defined and well behaved and A boundary value problem which satisfies these three requirements is said to be well posed in the sense of Hadamard, who introduced this concept in his 1920 lectures at Yale University. So section 4 then, if that introduces boundary value problems, section 4, the method of separation of variables, is when we get to substitution and the transformation of coordinates and transformation of variables, it's going to be a very, very useful thing because it makes it possible to reduce otherwise kind of unsoluble integrand with something that has a really clear form, as long as the transformation of coordinates holds up and the substitution of variables holds through in this composition of functions, which makes it like so. But separation of variables is another key usual reasoning about solving these variables, solving these systems. We shall now seek a solution for a specific BVP involving the heated bar. If d and d bar are, as an example 1.1, find a continuous function u from d bar to r that is of class C2 in D, and such that u sub t equals k u sub xx, u of 0 comma t equals 0, u of a comma t equals 0, and u of x comma 0 equals fx for x between 0 and a inclusive, where f is a given continuous function. We shall look for a solution of the form u of x comma t equals x of x t of t. So he's named functions x of t, and so he's defined things in terms of, this is where we get into separation of variables and also the different frequency and phase components. We'll get into this various settings of the orthogonal functions and why, when their pairs are together, that you can have the spectral analysis about the one or the other, that all this families of the transforms in the worlds of what are called the methods and analytical differentiation of these transforms show up. Mellon's, Henkel's, Z-transform, Fourier transform, up into the wavelets. There's many applications up in wavelets. We shall look for a solution of the form u of x comma t equals xt, where x and t are unknown functions to be determined. There's no reason to assume a priori that the solution will be the product of a function of x alone by a function of t alone. This is what we talk about in this previous talk about the interaction of terms. And so there's definitely been a lot of skipping around in terms of these definitions and the milieus and the setups, the ansaetze of all these differential systems, and with regards to the linear systems, and with regards to all kinds of the ways to get figured out that they're like solutions is via the tautochrone or the isochrone, and these being the old-fashioned words for systems that could be built with geometry and the tools of geometry and sticks and string and maybe measurements off of some playing of notes or the harmonic, where the tautochrone or isochrone made it possible to define what happens in the given same amount of time, where these differential systems are almost always parameterized by time and reflect this restitution and oscillation and dissipation and attenuation in time. So anyways, even as far back as the ancient Greeks or in the time of Galileo, some of these solutions were had calculators that solved them, analog calculators, which were basically in terms of marking out by the logarithmic or some of these other scales, these things, and then just being able to trace that out in as a manner of rubber bands or the spirograph or the pantograph or the tautochrone or the isochrone, that make it possible to solve some of these otherwise things that are otherwise just subject to analytical methods. And so when you talk about separation of variables and when the x and t are separate functions, and so you can kind of compute, it's like, well, resistance begins at x and then acceleration is in terms of t or something like that. Then we can think about a way to separate the variables, but when they're combined in terms of their interactions at the beginning and end is for defining ways to separate the variables that are just separate in the center, but on either end become their mixed terms or cross terms. These are things. Here, separation of variables, there's no reason to assume In searching for a solution in this form, Fourier was inspired by a similar method of attack employed by other mathematicians before him, notably D'Alembert, whose work we shall present in Chapter 5. The ultimate justification of such a method, which is, as might be expected, is not applicable to all boundary value problems, is provided by the fact that it does indeed work in many cases of interest in mathematical physics, or you can use it as an approximation. Or you can just make it in one function and another function, and then just have this kind of offhand function for everything else. In terms of however so far you can parameterize the one in terms of the other and make implicits and results, and help work up and build out implicit solutions and all these kinds of things, which will establish parametric forms for integrals that will also collapse down to these things for solutions of optimization problems and such. If such a solution exists, the heat equation implies that xt prime equals u sub t equals ku sub xx equals little k x prime prime t. For x comma t and d. If we further assume that x is not equal to 0 for x between 0 and a, and that t of t is not equal to 0 for t greater than 0, we obtain that t prime over t equals kx double prime over x. Now the only way for a function of t to equal a function of x is for both of them to be constant. Denoting this constant by negative lambda leads to the pair of ODEs t prime plus lambda t equals 0 and kx double prime plus lambda x equals 0. I've read through a similar development before, so I'm just kind of remembering my instructor's approaches to these things. A great instructor. Thus, the original equation in two variables has been replaced by two equations, each in one variable. That is, the variables have been separated, and this is what gives the method its name. The first equation has a general solution, t of t equals constant c of e to the negative lambda t, where c is any constant. Note that t is never 0, as we assumed above. The solution of this second equation depends on the sign of lambda. If lambda less than 0, and if we have put mu equals lambda over k, the general solution is x over x equals a times e to the quantity root negative mu quantity times x, all that in the exponent, plus b e to the all in this in the exponent negative root negative mu x. So those reciprocating terms, in a sense, build up about through these constants. Those in terms of the mu here, and I'm scanning backwards because I've lost track of mu. It's not introduced. That, oh, here it is. If mu equals lambda over k, and that's the proportionality constant over otherwise the diffusivity constant, and taking the root of it is for the quadrature, and that then is about the exponent, where a and b are arbitrary constants. But then the boundary conditions with u of 0 comma t equals 0 and u of a comma t equals 0 imply that a plus b equals 0, and a times e to the negative mu root negative mu a plus b times e to the negative root negative mu a equals 0. Now I don't know why he's got a in there and b in, and not b in the other one. I think that's a typo. Which in turn imply that a equals b equals 0. This leads to the trivial solution u equals tx is proportional to 0, which is indeed a solution, but only when f is proportional to 0. If lambda equals 0, the original equation reduces to x double prime equals 0, so that x of x equals a plus b x. That's when lambda equals 0, it reduces. So having this constant defined from rewriting the equations after algebraic transformation, when you have a formula defined by t prime over t, those two functions, so it's derivative, and it's kind of in a sense rederivative, because when something goes in that is a function of the derivative, it becomes a thing, and it's about the exponential, where it wouldn't have vanishing terms of the one and the other, or the spiral space flowing curve, or the original would be like an impulse in that. So that gets into what's the difference when it's at 0 and going to and from 0. Well, it's at 0. Well, that's trivial. Don't try to get there. You know, in terms of that, well, how does it come up from 0? It's like, I don't know, start at non-zero. Anyways, these are some kinds of things I'm looking at with regards to this development of the separation of variables. And the separation of variables by the combining of the derivative forms and making more higher order derivative forms. T prime over t is the derivative over the function itself, is a higher order, in a sense, derivative form. Even though algebraically then it's just kind of let out. This leads to the trivial solution u equals tx equals 0. As before, the boundary conditions lead to a equals b equals 0 and to the trivial solution. Therefore, if f is not proportional to 0, it must be lambda greater than 0. In this case, and again and this kind of reflects what I just said. In this case, and again with mu equals lambda over k, the general solution is x of x equals a sine root mu x plus b cosine root mu x. And this is where it's nice that the lambda was brought in as negative or what, so that these result not all complicated and contrived in the Fourier. But it could be kind of different if that was to be in terms of like 1 minus sine x or 1 minus cosine x. We now deduce from the boundary conditions that b equals 0 and a sine root mu a plus b cosine root mu a equals 0. So I guess that is in terms of a. I mean, it's used consistently twice. I would just expect it to be in terms of b again, because it's in terms of the constant b. Oh no, because a is just a bound. I have to confuse myself less, because that's all that is. That's just the length. A is the length. The system is between 0 and a. Unless big A equals 0, in which case we obtain the trivial solution once more, it must be that root mu of a equals n pi, because of that mu is lambda over k, and that n pi is about the half period of the period of revolution of that the period of revolution is 2 pi, and that n pi is a solution when root mu a equals n pi, that it defines n pi in terms of root mu a. Hence we can obtain infinitely many solutions, each of the form x of x equals a sub n, the sequence now, or the series, say, as so defined, of sine of n pi over a times x. The constant a sub n can be chosen arbitrarily for each n. Note then that non-trivial solutions have been found only for values of lambda of the form lambda equals mu k equals n squared pi squared over a squared k. That gets back into why there's the negative root mu, negative mu. That is root of mu is because that's why it sets up this lambda equals mu k is defined in terms of n squared pi squared over a squared k, because it's almost as where n pi over a k squared, that whole quantity root, and that gets into, as we've been talking about the quantities of things, that it's true that the reduced form of a quantity is maybe dimensionless, and maybe after dimensional analysis it's a proper thing to be, and sometimes the quantities are essentially built up in terms of these higher order quantities, or any conventions in the quantities, anything to do with any of the quantities, that the quantities in the systems of equations, in the system of formulas, make it so that just because it can be reduced doesn't necessarily mean that it can be reduced without loss of information, without loss of generality, or without introduction of too much generality or not enough. Anyways, for each of these, and if we recall the solution to the equation in T, we conclude that the heat equation has a non-trivial solution. U sub n x con t equals c sub n e to the negative n squared pi squared kt over a squared times quantity sine n pi over ax. So here it almost gets in where there's a traditional linear way to write everything. And so it might make as much sense to write them in terms of, besides to just write exp instead of e to the and having the superscript, all this carriage. And otherwise there are neat traditional normal ways to write all the things. But then in terms of that being the product of two functions, and then is about how the variable n is the same in both of them, and the variable a is the same in both of them, and the pi term is relevant to both of them. That gets into various ways to write that, and then various ways to write transforms that attain to that and make it so that it's about the same thing, from other trivial cases that build up to emergent cases of a sort make of these things. This is my reading from reading so far, the development, the separation of variables as for the initial and boundary value problems for the Fourier heat equations, and the constant propagation of energy from one location to another according to given tendencies and propensities of given values to reflect differences, and from those to reach equilibrium according to stable and astable equilibriums. I mean, it's assumed that it's not like a blob of heat shoots from end to end and bounces back off it before it even gets through it. Although you can imagine a contrived way where that is so, in terms of like a kind of ergion or something in terms of heat, like a particle, like a phonon or something like that. Now that's just saying that besides these linear solutions is the idea of how to make it up and so that it's pretty much just so for a bunch of other kinds of things that it can at least be described, and then to figure out how those get analog computed easier, and then when they can be used in terms of composition of those, basically behavior at the ends vis-a-vis behavior in the middle, to compute the ends laboriously and figure out what's going on with them in terms of the middle, and have that be pretty much a stroke. Where c sub n of the quantity c a sub n is just an arbitrary constant. Each of these solutions is of class C2 and has a value 0 for x equals 0 and x equals a. Perhaps it has been noticed that the solutions we found for x above have zeros, contrary to the starting assumption that x sub x is not equal to 0 for x between 0 and a. But this is no obstacle because it's easily verified by differentiation that u sub n is indeed a solution of the heat equation. What matters then is that we have found such a solution. What does not matter is that certain steps of our procedure were unjustified. In fact, this is not untypical of work in applied mathematics and will be a recurrent theme in this book. When looking for the solution of a particular problem, we will not hesitate in making any number of reasonable assumptions, justified or unjustified, and if they lead to a solution that can be verified a posteriori, the matter is settled, and that is that. So here the author is just saying, as long as you can check, this is called check. And what you do is you use whatever methods you can, and then you arrive at a solution, and then you compute check. And if it fails, then not only were you justified in your assumptions, but also took the wrong one. And so what he's describing is going to be so for various cases, but it also kind of, it reflects a certain contrast with his Hedemard's bit about that the well-posed problem should change only by a small amount, and with regards to around 0, and then also how to approach something like that with regards to, as was mentioned, like the exponential case in the ratios of the first order differential with respect to a function, and the original case, or the impulse and the drop off, or what, that make it so that the results, kind of like when you really enjoy log linear and you say, I've computed something and it's proportional log. What does that mean? It's like, well, in my log linear paper, it looks like a straight line. The idea is to figure out how to make it so that it was like, well, what is this like? It's like, well, it's really bumpy in the beginning and then it just goes on forever. The idea is to figure out how to make that so that in the beginning it looks kind of like a straight line, and at the end it kind of looks like a straight line, in the middle it looks like a straight line. But here the author is making clear that it's like, yeah, you can say I divided by 0, but now it's gone. And that's on you to check it, and I'll be checking all the time. And so basically the author just lets us know that he considers this sound, and it's sound in the sense that if you find a check, you can inspect any function and find if it's a solution to this integral by taking its derivative and seeing what's so. Besides constants or whatever, and then making sure that the values are well defined in terms of like so. And then in terms of that being so for like a system of like one equation is one thing, but then in terms of the transformation and the collection of variables, then you can never get lost underneath the stack, that otherwise then you lead to what are called pathologies or bad things. But as the author puts it, and I would agree that you when you're using usual methods of analysis in differential equations, that when you found a solution, it involves checking it. Okay, then we get in section 1.5 is linearity and superposition of solutions. So this is usually a couple days course, and so this text is that was noted in the preface. It's for the advanced graduate student, or this is like Calc 12 or whatever, what we're going to get into later in this, but I am still trying to just recall my introduction to differential analysis. And also I'm looking for all kinds of these conditions, what I can work up, because these are very general solutions. These end up saying, hey, anything you get, you can try and solve this way. Anything you get, you can try and solve this way. So what I'm looking for is some of my older, simpler boundary value problem books, and I have a variety of sources here, and this is something I've been looking at, this PDE's basic theory, and this contributions to nonlinear PDEs, and where we've been talking about the Lagrangians and the Lagrangians and the differentials and these and that. Ordinary differential equations. That then this is where I'll leave off, as we've gotten what's left in this chapter 1 is linearity and superposition of solutions, and about how to pick those out. While Fourier's arguments and examples were overwhelming and sufficiently convincing to merit the Institute's prize for 1811, the fact remains that he did not provide a mathematical proof of his assertions. We shall devote the next chapter to study the convergence of trigonometric series and the conditions in which their sum can equal an arbitrary function. So what will happen is that Fourier's series are defined, these analytical series, And we're going to talk about how that fits in with differential geometry and what it means that there are various conditions, there are various beginnings and endings to these things, and various parameterizations of the implicits in solutions, which lead to lots of particular solutions, and means to get more closed forms besides what can usually result a series of coefficients that can be computed, that can be crunched, and according to which approximations can be computed. Because if closed form is possible, it's generally preferable, and especially insofar as where it's resistant to small changes in domain causing arbitrarily large changes in the range of the solution's value from the problem's value. Well, anyways, that's what for today. I hope this differential course will get into some interesting things, because what I'm trying to figure out is in terms of log x and 1 over x and its derivative, what else is going on in terms of what I have as a factorial exponential identity and the original analysis of functions that are their own antiderivative. Because usually all these families of functions that are shown out is like, you can always use e to the x. E to the x is totally central to all this differential analysis because it's its own antiderivative. And so when it falls down to, you get off after e to x and ln x, and you take the inverse reciprocal of that, and you use e to the x. I need to find the integral. We'll make a derivative and then take the antiderivative, you know. And so trying to figure that out with any other setup of a function or formula that can be its own antiderivative will be part of the course. Well, great. Have a great day. So.